Hello, I'm Oumayma Rachidi, PhD student at Moulay Ismail University in Morocco. Today, I'm delighted to share our paper entitled The Stereovision System for Real-Time Person Detection in ADAS Applications using a fine-tuned version of YOLOv5. This research was conducted with the guidance and support of Professor Chafik Ed-Dahmani and Professor Badr Bououlid Idrissi. So object detection constitutes a fundamental component within the field of computer vision, playing a crucial role in various applications, such as surveillance, medical and healthcare systems, and advanced driver assistance systems, or ADAS. In the context of ADAS, the precise identification and localization of obstacles is imperative to avoid collisions and ensure a safe driving. Among the paramount of obstacles in the context of ADAS are persons, encompassing pedestrians, cyclists, and riders, necessitating accurate and fast detection to facilitate reliable decision-making processes. Person detection should be complemented with distance estimation, which is crucial in ADAS applications, as it equips the system with comprehensive data for executing necessary actions and ensuring safe driving practices. However, pedestrian detection emerges as a critical task within the domain of computer vision, presenting inherent challenges such as occlusion, low-quality image, and detection under various lighting conditions. Besides, cyclists and riders are equally crucial for ensuring road safety, and therefore they should also be detected accurately. And person detection in the context of ADAS should be complemented with distance estimation, as detection alone is not sufficient for a comprehensive safety approach. To address these challenges, we worked on the design of a stereovision system using an economical, energy-efficient, and highly effective device, which is the Raspberry Pi 4. We also proposed an approach for real-time person detection across various contexts using transfer learning embedded on the same economical, energy-efficient, and highly effective AI device. And we worked also on the creation of a custom dataset to train the model using augmentation techniques to develop a robust model for person detection. So as mentioned, pedestrian detection emerges as a critical task within the domain of computer vision, presenting inherent challenges. Recently, many research have addressed one or some of the challenging factors, and the majority of this research have been focusing on the utilization of deep neural networks. Examples of these studies are the occlusion-aware RCNN to enhance the detector's accuracy within crowded scenes. We had also the multispectral pedestrian detector based on SSD, prompting the utilization of thermal images to address pedestrian detection challenges during nighttime scenarios. Also, we had the fast focal detection network, or F2D-net, specifically designed to enhance the performance of two-stage detectors, and the localized semantic feature mixers for efficient pedestrian detection in autonomous driving, which is called LSFM, and which was designed to address challenges associated with small or heavily occluded pedestrians. So in contrast to these studies, we worked on fine-tuning YOLOv5's model for person detection in various environmental conditions, prioritizing simplicity and efficiency. So the device system was designed in our laboratory utilizing a 3D printer. The stereoscopic camera that we are seeing here is composed of two OV5647 5 megapixels cameras, and it was developed as a component of this system. Operational control is facilitated by a Raspberry Pi 4 Model B, employing computer vision techniques to provide real-time video incorporating person detection based on the fine-tuned YOLOv5 model. The stereovision cameras were used for their ability to acquire high-resolution images containing detailed visual information, including colors and shapes, and it proves essential for applications related to object detection. The two cameras were calibrated to enhance image quality by eliminating distortion and ensuring rectified images. So for the YOLOv5 object detection model proposed in this work, it represents noteworthy iteration in the evolution of object detection methodologies within the field of computer vision. It has gained substantial attention for its innovative architectural design, which combines efficiency, accuracy, and real-time processing capabilities. The model incorporates a CSP Darknet 53 as a backbone, contributing to improved feature extraction capabilities, and the path aggregation network, or PANET, for enhancing feature fusion across different scales, enabling robust object detection and allowing YOLOv5 to excel in scenarios with varying object scales and complexities. To fine-tune the YOLOv5 model, we developed a custom dataset for person detection, which was generated by building upon the COCO dataset. So approximately 40,000 training images and 2,758 validation images were selected from the COCO dataset with a specific emphasis on the person class. To enhance the robustness of the detector and address common challenges in person detection, extensive data augmentation techniques were employed. First, a 20% decrease in brightness was implemented as an augmentation technique to improve the model's resilience to lighting challenges, particularly during nighttime scenes. A Gaussian blur was also applied to improve the model's adaptability to camera focus issues, and it was of 2.5 pixels, and a noise level up to 2% of pixels was applied to foster the model's resilience to camera artifacts. By implementing these techniques, we generated a dataset of 118,425 training images and 2,758 validation images. So the process flow of our system is depicted in this figure. For the training phase, the custom dataset is used to retrain YOLOv5, and the training and testing are performed using Google Colab. For the implementation phase, we first set up the necessary libraries for implementing the YOLO model, and then we loaded the customized weights generated from the fine-tuning process, and we performed the video capture utilizing OpenCV library, and we implemented the model for each frame. So in the case of pedestrian detection, bounding boxes are generated by the YOLO model, and the outcomes are displayed on the screen of the Raspberry Pi. If no person is detected, then we go to the next frame. So as mentioned, the training and evaluation of the model were executed through the utilization of Google Colab. The validation set was employed for the computation of validation metrics, and the results revealed the high performance of our fine-tuned model in detecting persons across diverse scenarios. To assess the efficacy of our methodology, we use the following metrics: precision, which is true positives per true positives plus false positives; recall, which represents true positives per true positives plus false negatives; average precision, which is defined by this equation where n is the number of threshold, and PR and RC refer to precision and recall respectively. Then we had also the mean average precision, or MAP, which denotes the mean of all average precision through different object classes. In the context of our study, focusing exclusively on the person class only, this metric aligns with the average precision. So here in this figure, we have the fluctuations of key metrics through different training epochs, where we can see the metrics mentioned earlier: the precision, the recall, the MAP05 and MAP05095, in addition to object loss function, which evaluates the algorithm's ability to predict the presence of an object. Also, the box loss, which assesses the alignment of bounding box with ground truth, and the class loss, which reflects the accuracy of the algorithm in predicting the object class. So the analysis of this figure indicates the effective fine-tuning of the model with the initial epochs reflecting the performance of the pre-trained weights and the subsequent epochs illustrating progressive enhancements achieved through the fine-tuning process. To further evaluate the detector's performance, the precision recall curve was generated from different confidence score values, and as we can see here, a decline in the confidence score is linked to a proportional rise in the recall, and conversely, an elevation in the score is accompanied by an increase in the precision. This table displays the outcomes derived from our approach. So we achieved the precision of 79 percent, a recall of 67%, an MAP05 of 76%, and an MAP05095 of 49%. And to further underscore the effectiveness of our approach, we conducted a visual comparison, and the figure here demonstrates the enhanced accuracy achieved through the fine-tuning process. Here we have real-time frames taken by our cameras, and of course we can see the high performance of the fine-tuned model in detecting persons. So as a conclusion, we can say that the detection of pedestrians, cyclists, and riders poses considerable challenges within this domain, involving both person detection and distance estimation. This paper presented a stereovision system specifically designed for person detection within the context of ADAS using a YOLOv5 fine-tuned model. The obtained results reveal high accuracy with an MAP05 reaching 76.2% and an MAP05095 of 49.2%. Further work will extend to encompass depth estimation utilizing the stereo camera, as well as exploring the utilization of a higher computational resource instead of the Raspberry Pi. Additionally, adjustments will be made to implement the system in an electrical vehicle, simulating diverse functionalities along with person detection and distance estimation. Thank you.